Beneath the bark of every tree, a quiet record is being kept. A diary written not in words, but in wood. Welcome to the Sleepy Lab. Tonight, we will drift through the hidden life of trees, how they sense the turning of the year, how they remember every season they have ever lived. If this channel helps you rest, consider subscribing, one sleepy soul at a time. Now, let's begin. Every year, a tree adds a new ring of wood just beneath its bark. One thin, quiet circle laid down slowly over the course of a single growing season. It does not rush. It does not skip a year. It simply grows. And in growing, it remembers. No two of these rings are ever quite the same. One year may bring long rains and warm sun, and the ring grows wide. Another year may bring drought, or cold that lingers too long into spring, and the ring is narrow, barely there. Each ring is a portrait of the year that made it, a record of what the sky offered and what the earth could give. A tree does not feel the seasons the way an animal does. It does not shiver in the cold or seek shade in the heat, but it responds to every shift with a kind of chemical precision, quiet and exact. Molecules moving through its tissues like whispered instructions. When autumn comes to a deciduous forest, something deliberate begins. The trees do not simply lose their leaves, they let them go through a careful process called abscission. At the base of every leaf stem, there is a thin layer of cells, so small you would never see them with your eyes alone. And as the days shorten, these cells begin to change. They slowly seal themselves shut, building a barrier between the leaf and the branch. It is not damage. It is not decay. It is a gentle closing, like a door eased shut at the end of a long evening. Before the leaf falls, something beautiful happens. The green begins to fade. Chlorophyll, the pigment that spent all summer catching sunlight, starts to break apart, and as it disappears, other colors emerge. Yellow, orange, pigments that were there all along, hidden beneath the green, now finally visible, like stars appearing as the last light leaves the sky. But not all autumn color was waiting in hiding. The reds and purples that blaze through some forests are something different. These come from pigments called anthocyanins, and the tree makes them fresh, actively producing them in the fall, as if painting one last gesture before the quiet sets in. Why would a tree spend energy making new pigments just as it is preparing to shed its leaves? Some scientists believe these anthocyanins act as a kind of sunscreen, shielding the leaf from bright light during those final days when the tree is still pulling nutrients back from the leaf into its branches. A small act of protection, so nothing is wasted. Not every tree surrenders its leaves to autumn. Evergreen conifers, the pines and spruces and firs, keep their needles through the coldest months. They manage this by filling those needles with compounds that work like antifreeze, lowering the point at which their tissues would freeze, holding life steady even when the air turns bitter. If you have ever held a pine needle between your fingers, you may have noticed it feels slightly waxy. That coating is there for a reason. It reduces water loss during the cold, dry months when the ground may be frozen and the tree cannot easily draw moisture from the soil. A thin shield of wax. Winter is a difficult time for trees in temperate forests, even the ones that keep their leaves. They can lose over 90% of their ability to conduct water through their wood. The vessels that carried water so freely in summer become blocked or emptied. The flow slows to almost nothing, and the tree waits. This waiting has a name: dormancy. But dormancy is not sleep. It is not a tree simply doing nothing until the weather improves. It is a highly regulated state, a kind of suspended growth, carefully controlled by hormones and chemistry. The tree is still alive in every cell, still sensing, still responding, just holding still. And here is something quietly remarkable. A tree cannot simply wake up whenever it feels warmth. It requires a specific number of cold hours first, hours spent below a certain temperature, accumulating slowly through the winter. This is the tree's way of making sure it does not wake too soon. that a few warm days in January do not trick it into budding before the last frost has passed. This requirement is called vernalization, and it is different for every species. A peach tree may need about 800 hours of cold. Some apple trees need over 1,000. The tree counts the cold in its own quiet way, not with numbers, but with chemistry, molecule by molecule, until the threshold is met, and something deep inside it shifts. Until then, it rests, holding its miniature leaves and flowers already formed inside its buds, waiting for the signal that spring has truly come. And so the tree stands in the winter dark, still, patient, its rings of memories circling inward, each one a year, each one a story told in wood. But there is a quiet danger woven into this arrangement. If winters grow too warm, if the cold hours never fully accumulate, the tree may reach spring without having met its threshold. And when that happens, something subtle goes wrong. The buds hesitate. The bloom comes late, or thin, or not at all. Orchards that once flowered reliably begin to falter, not from disease, not from neglect, but because the winter was not cold enough, not long enough, to satisfy the tree's ancient requirement. It is a strange kind of loss, a season that was too gentle for the tree to bear. And yet, even now, in the deep of winter, the tree is not empty. Far from it. Inside each bud, formed months ago in the fading light of late summer, there are already leaves, already flowers, miniature, tightly folded, pressed together like pages in a book no one has opened yet. They have been there since August, some of them, waiting. Complete in form but held in stillness, wrapped in scales that shield them from ice and wind and drying air. All through autumn they waited, all through the first frost and the second, through the shortest day of the year and the longest night. They are waiting still. And what holds them so perfectly in place, what keeps them from unfurling too soon, is a molecule, a hormone called abscisic acid. It moves through the tree quietly, steadily suppressing growth, keeping each bud sealed, each cell paused at the edge of division, but not yet dividing. Abscisic acid is the voice that says not yet, the hand held gently over the door. It does not stop life. It holds, and the tree listens through December, through January, through the long, blue silence of February. But slowly, so slowly it would be impossible to notice from the outside, something begins to shift. Another hormone, one called gibberellin, starts to rise. Gibberellins are the opposite whisper. They speak of growth, of stretching, of reaching upward and outward. Their levels climb as the cold hours accumulate, as the days begin, almost imperceptibly, to lengthen. And so, the fate of each bud, the timing of each new leaf and every flower, comes down to a balance, a quiet negotiation between two chemical signals, one saying wait, the other saying soon. Abscisic acid and gibberellin. They do not compete. They converse, and the tree holds both messages at once, weighing them the way a river weighs the slope of the land beneath it, not with thought, but with something just as precise. When the balance tips, when gibberellin finally rises above the fading voice of abscisic acid, the bud begins to swell. The scales soften. The tiny folded leaves inside start to press outward, and spring, at last, arrives, not as a sudden event, but as the resolution of a conversation that has been going on for months. But hormones are only part of the story. The tree also listens to light. Not the way we do, not with eyes, but with proteins, tiny, ancient molecules embedded in its tissues, sensitive to wavelengths of light we can barely distinguish from one another. One family of these proteins is called phytochrome. Phytochromes respond to red light, and to a slightly different wavelength called far red light. The ratio between these two, the balance of red to far red reaching the tree, changes throughout the day and throughout the year. In the evening, as sunlight passes through the atmosphere at a low angle, far red light increases, and the phytochromes register this shift. They change shape, literally, folding into a different form depending on which wavelength they last absorbed. Through this quiet transformation, the tree measures something remarkable. It measures the length of the night. Not the brightness of the day, but the duration of darkness. And this changes with the seasons. In summer, the nights are short, and the phytochrome signal tells the tree to keep growing, to stretch its branches, to build more leaves, to gather as much light as it can while the sun is generous. But as summer fades, as the nights grow longer by a minute, then 2, then 5, the signal shifts. The phytochromes register the change, and the tree begins to prepare, slowly pulling nutrients from its leaves, slowly building the buds that will carry next year's growth, slowly turning inward. Long nights are the tree's calendar, more reliable than temperature, which can swing wildly from day to day, more steady than rainfall, which comes and goes without pattern. The length of the night is constant, predictable, faithful to the tilt of the earth and nothing else. And so the tree trusts it. But phytochromes are not alone in this work. There is another family of light-sensitive proteins called cryptochromes. These respond not to red light, but to blue, the short, bright wavelengths that fill the sky on a clear morning. The cryptochromes help the tree sense the quality of light, its intensity, its direction, the subtle difference between the blue of early morning and the blue of late afternoon. Together, phytochromes and cryptochromes give the tree something extraordinary, a detailed, layered portrait of the light around it, not just whether it is day or night, but how long the night has been, how strong the sun is, what angle it arrives from, whether the season is advancing or retreating. All of this without eyes, without a single nerve. Just proteins, folding and unfolding in response to photons that have traveled 93 million miles from the surface of a star. And the tree reads them, the way your hand reads warmth from a fire, not with understanding, but with perfect, quiet accuracy. So when you picture a tree in winter, standing bare against a gray sky, know that it is not simply enduring the cold, it is measuring it, counting it, sensing the light even on the darkest days, holding its tiny folded leaves and waiting, balancing one hormone against another. It is doing all of this in silence, in stillness, in the dark. And it has been doing it for a very long time. Now, not every tree on Earth keeps this kind of record. In the tropics, where the air stays warm and the rains come often enough, some trees grow continuously, month after month, year after year, without ever pausing, without ever entering dormancy. And because they never stop, they never form distinct rings. Their wood is smooth, and even all the way through, a single unbroken column of growth with no chapters, no markers, no way to count the years by looking inside. It is as if someone wrote a diary, but never started a new page. The words are all there, but they run together, one long sentence stretching across a lifetime. Trees in temperate forests are different. They pause, they rest, and every time they begin again, they leave a mark, a ring, a thin, quiet line drawn in wood, recording the fact that another year has passed, another winter was survived, another spring arrived. And there is an entire science built around reading those lines. It is called dendrochronology, the study of tree rings, and it is one of the most precise methods we have for understanding the past. The idea is simple, but the results are extraordinary. Each ring reflects the conditions of the year it was formed. A wide ring suggests a good year, plenty of rain, warm temperatures, a long growing season. A narrow ring tells a harder story, drought perhaps, or fire, or the shadow of volcanic ash dimming the sun, or the slow devastation of insects feeding on leaves that should have been making sugar. Every ring is a sentence, and every tree is a book. But here's what makes dendrochronology so powerful. Trees in the same region, experiencing the same weather, the same droughts, the same cold snaps, tend to produce similar patterns of wide and narrow rings. The sequence is not identical from tree to tree, but the rhythm is recognizable. The way two people humming the same melody will not sound exact. Scientists use this. They take a core sample from a living tree, a thin cylinder of wood pulled gently from the trunk, and they read the pattern of rings. Then they find an older tree, perhaps one that fell long ago, or a beam of timber in an ancient building, and they look for where the patterns overlap. Where the rings of the dead tree match the rings of the living one, they can link the two records together, extending the timeline further back. And then they find an even older piece of wood and match it to the one before. Ring by ring, tree by tree, overlap by overlap. Scientists have built continuous records that stretch back thousands of years. The oldest known unbroken tree ring chronology reaches back more than 12,000 years, into the final centuries of the last ice age, assembled from living trees, fallen logs, and ancient wood preserved in bogs and riverbeds across Europe. 12,000 years of seasons, recorded in wood, read by patient hands. And some of the trees that contributed to these records are still alive. In the White Mountains of California, at elevations where the air is thin and the soil is mostly stone, there are bristlecone pines that have been growing for over 5,000 years. They are among the oldest known living organisms on Earth, gnarled, twisted, stripped of bark on most of their trunks. They do not look like much, but they have been standing there since before the pyramids were built, before writing was invented, adding one thin ring each year, slowly, quietly, without hurry. Their rings are narrow, sometimes barely visible, because life at that altitude is spare. But every one of them is there, counted, dated, verified. And within those rings, within the rings of all trees, there is something else, something invisible but profoundly useful. Carbon. Specifically, a rare form of carbon called carbon-14, a radioactive isotope created high in the atmosphere when cosmic rays strike nitrogen atoms. This carbon-14 drifts down, is absorbed by plants during photosynthesis, and becomes part of their wood, locked into each ring at the time it was formed. The amount of carbon-14 in the atmosphere is not constant. It fluctuates over centuries, influenced by solar activity, by the Earth's magnetic field, by subtle shifts in cosmic radiation. And trees record these fluctuations, ring by ring, like a chemical calendar. Each ring captures a snapshot of the atmosphere in the year it grew. This has proven invaluable, because radiocarbon dating, the method archaeologists use to determine the age of ancient organic materials, depends on knowing how much carbon-14 was in the atmosphere at any given time. Without that knowledge, the dates it produces can drift, sometimes by centuries, but tree rings provide the correction. They give us a precise, year-by-year record of atmospheric carbon-14 stretching back millennia, allowing scientists to calibrate their measurements. A volcanic eruption in 1815, the eruption of Mount Tambora in what is now Indonesia, was one of the most powerful in recorded history. It threw so much ash and sulfur into the upper atmosphere that global temperatures dropped the following year. Crops failed across Europe and North America. 1816 became known as the year without a summer, and in the wood of trees across the entire northern hemisphere, that year left its mark. A narrow ring, sometimes barely there. A whisper of stunted growth recorded in forests that had no idea what had happened on the other side of the world, but felt it all the same. That is the quiet power of a tree ring. It does not interpret, it does not explain, it simply records, faithfully, automatically, whatever the year brought. And all of this happens in one place. A thin layer of cells, no thicker than a sheet of paper, nestled between the bark and the wood. This layer is called the cambium, and it is where every ring begins. The cambium is alive. It is a ring of dividing cells that wraps around the entire trunk, just beneath the surface, and it is the only part of the trunk that is actively growing. Everything inside it is old wood. Everything outside it is bark, and the cambium sits between them, quietly building. In spring, when the days lengthen and water flows freely from the roots, the cambium begins to divide. It produces large cells with thin walls, wide open, designed for speed, for rushing water upward to the new leaves as fast as possible. This early growth is called early wood, and it is light in color, soft in texture, full of space. But as summer deepens and the urgency of spring fades, the cambium shifts. The cells it produces become smaller. Their walls grow thicker, denser, darker. These are built not for speed, but for strength, for holding the tree upright through autumn storms and the weight of winter snow. This is late wood, and it is tough, compact, resilient. The visible difference between the pale early wood and the dark late wood, that gentle transition from light to dark within a single year of growth, is what creates the ring. It is not a line drawn by the tree, it is a boundary, a place where one summer ended and the next spring had not yet begun. A pause made visible, a season remembered in wood. Not every tree writes its rings in the same way. An oak, if you were to look at a thin slice of its wood under a microscope, would show something striking in each ring. The early wood is filled with large open vessels, wide as tiny tunnels, clustered together near the start of the growing season. Then the late wood that follows is dense and tight, with almost no large vessels at all. This pattern is called ring porous, and it gives oak wood that bold, dramatic grain, those sweeping lines you might recognize in an old table or a heavy door. A maple tells a different story. Its vessels are smaller, and they are spread evenly throughout the entire ring, early wood and late wood alike. There is no sudden shift from open to closed, no dramatic contrast, just a quiet, even texture from one side of the ring to the other. This is called diffuse porous wood, and it gives maple its smooth, fine-grained character. Two trees, two ways of remembering the same season, one in bold. Now, if you could look at the full cross-section of a trunk, you would notice something else. The outer rings, the ones closest to the bark, are usually lighter in color. This is the sapwood, and it is alive. Every cell in the sapwood is working, pulling water from the roots, passing it upward, ring by ring, toward the canopy far above. The sapwood is the tree's circulatory system, its living pipeline. But move inward, toward the center of the trunk, and the wood begins to change. It grows darker, sometimes deep brown, sometimes reddish, sometimes nearly black, depending on the species. This is the heartwood, and it is no longer alive in the way the sapwood is. It no longer carries water. Its vessels have closed. Its cells have finished their work. But the tree does not simply abandon this old wood. Instead, it fills it with other things: tannins, resins, oils, compounds that resist decay and repel insects. The heartwood becomes a kind of archive, chemically preserved, structurally essential. It is the backbone of the tree, the dense core that holds everything upright, even though it no longer participates in the daily business of living. The sapwood drinks, the heartwood stands. Together they make the trunk whole. And the drinking, the movement of water through that living sapwood, is something quietly extraordinary. A large oak on a warm summer day may pull more than 100 gallons of water from the soil, up through its roots, through the sapwood, and out through its leaves. 100 gallons, rising silently, without a pump, without a heart. How does it happen? Part of the answer lies in the roots. In some trees, especially in spring, the roots generate a gentle pressure, pushing water upward into the trunk from below. This root pressure is modest, not nearly enough on its own to lift water to the top of a tall tree, but it helps. It gives the column of water a nudge. The real force, the one that does most of the work, comes from above, from the leaves. When a leaf opens its tiny pores to take in carbon dioxide for photosynthesis, water vapor escapes. This is transpiration. And as each molecule of water leaves the surface of a leaf, it pulls on the molecule behind it, which pulls on the next, and the next, all the way down through the branches, through the trunk, through the roots, and into the soil. This works because water molecules cling to one another. They are cohesive. They hold hands, forming an unbroken chain that stretches from the deepest root to the highest leaf. A single continuous thread of water, sometimes rising 100 feet or more, drawn upward by nothing more than evaporation at the top and the quiet loyalty of one molecule to the next. It is one of the most elegant systems in all of biology, and it happens in silence, in every tree, on every warm day, without anyone noticing. But this system is fragile. When winter comes and the soil begins to freeze, the water supply slows and sometimes stops. The columns of water inside the tree can break. Air seeps in, forming tiny bubbles that block the vessels. These are called embolisms, and they are a real danger. A vessel filled with air can no longer carry water. By the end of a hard winter, many of a tree's water-conducting vessels may be blocked this way. The tree enters spring with a damaged system, a network full of gaps. And yet, the tree has ways of beginning again. Some species, like birches, generate strong root pressure in early spring before the leaves have even opened. This pressure pushes sap upward with enough force to refill empty vessels, dissolving the air bubbles, restoring the flow. You can sometimes see this if a birch branch is broken in early spring. Sap will drip steadily from the wound, pushed out by that quiet pressure from below. Sugar maples have their own version of this renewal, and it is tied to one of the most particular rhythms of late winter. During the cold months, sugar maples store starch in the living cells of their sapwood. It sits there, inert, waiting. Then, as late winter arrives and the days begin to warm just slightly, something shifts. When temperatures rise above freezing during the day and drop below freezing at night, the starch begins to convert into sucrose, into sugar. This freeze-thaw cycle creates pressure inside the tree. During the day, as the wood warms, gases inside the trunk expand, and the sweet sap is pushed outward and upward. At night, as the wood freezes again, the tree draws moisture back in from the roots, reloading, preparing for the next day's flow. This is the rhythm that maple syrup harvest depends on. Those cold nights and mild days of late winter, the sap rising and falling with the temperature collected drop by drop from small taps in the bark. The sugar concentration in that raw sap is modest, only about 2 or 3%. It takes patience and heat to boil it down into syrup. But the tree is not making syrup for anyone. It is converting its winter stores back into usable energy, preparing to fuel the enormous effort of spring when buds will open, leaves will unfurl, and the whole system of water and sugar and light will come alive once more. All of this happening inside the quiet wood, beneath the bark, where no one sees. But the tree does not keep its struggles to itself. When the seasons press down, when drought tightens the soil, or insects begin to feed on tender leaves, a tree responds in ways we cannot see with our eyes. It speaks through chemistry. During the heat of summer, if a caterpillar begins chewing through a leaf, the tree may release volatile compounds into the air, tiny, invisible molecules drifting on whatever breeze passes through the canopy. These are not random emissions. They are signals carried outward through the warm air, reaching the leaves of neighboring trees. And those neighbors respond. They begin producing their own defensive chemicals, tannins that make their leaves less palatable, compounds that attract the predators of the very insects doing the damage. All of this unfolding in silence, tree to tree, without a sound. But the air is only one channel of communication. Beneath the forest floor, hidden in the dark soil, there is another network, one that connects trees at their... These are ancient organisms, thread-like filaments thinner than a human hair, that weave themselves into and around the roots of trees. The fungi receive sugars from the tree, energy produced by photosynthesis up in the canopy, and in return, they extend the tree's reach into the soil, gathering water and minerals the roots alone could never access. But the fungi do something more. They connect one tree to another, root to root, through miles of fungal threads lacing through the earth, forming a living network beneath the forest, sometimes called the wood wide web, a web not of light and electricity, but of sugar and water and quiet chemical exchange. Through these fungal pathways, trees can share what they have. A tree standing in a patch of sunlight may send surplus sugars underground to a neighbor growing in the shade. A tree rich in phosphorus may pass some along to one whose soil is poor. And this sharing crosses boundaries we might expect to be firm. It happens between different species, birch to fir, alder to cedar, connected beneath the surface by the same fungal threads. There are trees in the forest that scientists have come to call mother trees. These are the large, old, well-established trees whose root systems are vast and deeply connected to the fungal network. And research suggests that these mother trees may preferentially send nourishment to their own seedlings. The young trees growing in their shadow, struggling for light, receive a quiet gift through the soil, a share of sugar passed along the fungal web from parent to offspring. Not a conscious choice, but a pattern shaped by millions of years of living together in forests. And this network, like everything else in the forest, follows the rhythm of the seasons. In autumn, as the air cools and the soil temperature drops, the fungal threads begin to slow. Microbial activity in the earth decreases. The great underground exchange of sugars and nutrients grows quieter. The network does not die, but it rests, entering its own kind of dormancy, waiting, just as the trees above are waiting. Then spring comes. The soil warms, degree by degree, and the fungi stir. New threads extend outward. Old connections reawaken. The underground exchange begins again. Sugars flowing, minerals moving, the forest resuming its hidden conversation beneath the surface. This is a cycle as old as forests themselves. But the network depends on something the trees provide each autumn, something so ordinary we rarely think of it. Leaves. When a tree releases its leaves in fall, they do not simply vanish. They drift down, one by one, settling on the forest floor in soft, uneven layers. A single, mature tree can drop over 200,000 leaves in one autumn, 200,000 small packages of nutrients released from the canopy and laid gently on the ground. This leaf litter becomes a blanket, a rich, slowly decaying layer that feeds the entire soil ecosystem through the cold months. Within those fallen leaves are stores of nitrogen, phosphorus, potassium, the essential elements the tree drew up from the earth during the growing season, now returned. Decomposition begins almost. Fungi and bacteria soften the leaf tissue, breaking down the cell walls, releasing the nutrients locked inside. And they do not work alone. Earthworms move through the litter, pulling fragments of leaves down into their burrows, mixing organic matter into deeper layers of soil. Tiny invertebrates, springtails, mites, beetles no bigger than a grain of sand, all contribute to this quiet labor of breaking down what was once alive and making it available again. By the time spring arrives, much of the autumn's leaf fall has been transformed, woven back into the soil, ready to be taken up once more by roots and fungi and passed upward into new leaves, new wood, new growth. But before spring, there is winter to endure. And the forest has one more gift that helps it through the coldest months. Snow. When snow falls on the forest floor, it does not simply bury the ground, it insulates it. Fresh snow is full of trapped air, and that air acts as a blanket, holding warmth in the soil, even as the air above drops far below freezing. Beneath a layer of snow, the temperature at the soil surface may hover just around freezing, mild enough to protect the fine roots of trees, the fungal threads, the earthworms, the countless small organisms that live in the upper inches of earth. Without that snow cover, the soil can freeze much deeper, and the damage to roots and fungi can be severe. So the snow protects what the leaves have built. It holds the warmth in, keeps the soil ecosystem alive through the darkest months, until the days lengthen again and the slow thaw begins. All of this, the chemical signals drifting through summer air, the fungal networks pulsing beneath the soil, the leaves falling and returning their nutrients to the earth, the snow settling over everything like a quiet shield. All of it is the forest remembering. Not in the way we remember, not with thoughts or images, but with chemistry, with rhythm, with patterns repeated so many times they have become as reliable as breathing. Season after season, the forest gives and receives and gives again. And when the snow is absent, when a winter comes with cold but little cover, the soil lies exposed. The frost reaches deeper than it should, down past the surface, past the fine roots, past the delicate fungal threads that connect one tree to the next. The damage is quiet. No branches fall, no bark splits open. But below ground, the network frays. The smallest roots, the ones that do the most work, can be broken by ice forming in the soil around them. And the mycorrhizal fungi, those patient connectors, may not survive a deep freeze without the blanket they were meant to have. The forest feels this loss in spring, in slower growth, in roots that must rebuild what winter took. But even in the coldest months, even after every leaf has fallen and the branches stand bare against a pale sky, willows, for instance, if you were to look closely at a willow in winter, you might notice that its young branches are green, not brown, not gray, but a living, soft green. And that color is not decoration. It is chlorophyll, the same pigment that fills a summer leaf, tucked beneath the outer bark in a thin layer of cells called the corticular chlorenchyma. And on mild winter days, when a little sunlight reaches those branches, the willow photosynthesizes, gently, slowly, producing a small amount of sugar even without a single leaf. It is not much, but it is something, a quiet act of persistence. A tree making food from light in the middle of winter, as if it cannot quite bring itself to stop. This is one of the many small ways trees stay connected to the world around them, even when they appear to have withdrawn from it entirely. And perhaps the most remarkable connection of all is the one trees maintain with light itself. Trees at high latitudes, the birches and spruces of Scandinavia, the larches of Siberia, have evolved an extraordinary sensitivity to the length of the day, not the warmth of the air, not the moisture in the soil, but the precise number of minutes between sunrise and sunset. A difference of just a few minutes of daylight, a shift so small no human would notice without a clock, can trigger real physiological changes in these trees. A few minutes more light, and dormancy begins to loosen. A few minutes less, and the preparations for winter quietly accelerate. They measure this not with eyes, but with proteins, phytochromes and cryptochromes, molecules that absorb light and translate it into chemical signals. And what these molecules truly detect is not the day itself, but the night, the unbroken stretch of darkness between dusk and dawn. Trees are counting the hours of darkness, and when that count reaches a certain threshold, the season turns inside them. This response to the length of night, this ancient sensitivity, is called photoperiodism. It was first described in plants in the early 20th century, and it changed the way scientists understood how living things keep time, not by temperature alone, not by rainfall, but by the slow, dependable rotation of the Earth, and the way it tilts toward or away from the sun. The critical length of night that triggers dormancy is not the same for every tree. It varies by species, and more than that, it varies by where the tree's ancestors grew. A spruce from northern Finland responds to a different night length than a spruce from central Germany, even if they are the same species. The northern tree has learned, over countless generations, that winter comes early and stays long. Its threshold is lower. It begins shutting down sooner, preparing for cold that a southern tree would not yet expect. This is why a tree taken from a northern forest and planted in a warmer, southern place may behave strangely. It may drop its leaves too early, enter dormancy while the southern trees around it are still growing. It carries its homeland inside it, and this is why foresters take such care in matching seed sources to planting sites. A tree must be suited not only to the soil and the rainfall, but to the rhythm of light in the place where it will grow. Latitude matters. Local climate matters. The memory of where a tree comes from shapes how it will live in a new place. Memory. That word keeps returning. And it is not a metaphor. Not entirely. Trees do remember, not in the way we understand memory, not with images or feelings, but in a way that is, in its own quiet fashion, just as real. When a tree lives through a severe drought, something changes inside it, not just in that season, but in the seasons that follow. The wood it produces afterward may be different, denser, more resistant to water loss, as if the tree has learned from what it endured and adjusted its growth to be better prepared if it happens again. These changes are epigenetic. They do not alter the tree's DNA. The sequence of letters in its genetic code remains the same, but the way those genes are read, which ones are active and which are quiet, that can shift. Chemical markers attach to the DNA or to the proteins around it, turning certain instructions up or down, like adjusting the volume on different instruments in an orchestra. The melody is the same, but the sound changes. A tree that survived drought carries that experience in its cells, in the way its genes express themselves. And here is where it becomes something close to wonder. These epigenetic memories can sometimes be passed on through seeds. A tree that endured a hard season may produce offspring that are, from the very beginning, slightly better equipped to handle similar stress. The seedling has never known drought, has never felt its roots strain for water in dry soil, and yet it carries a kind of readiness, a preparedness inherited not through a change in its genes, but through a change in how those genes are read. It is not memory as we know it. It is deeper than that, and older. A way of passing experience forward without language, without thought, through nothing more than the chemistry of a seed. And so the forest is shaped not only by what is happening now, but by what happened before. Seasons that ended long ago still echo in the wood, in the roots, in the seeds, waiting in the soil. And those echoes are shifting. Over the past several decades, scientists have observed that spring is arriving earlier in many temperate forests. The moment when buds open and new leaves unfurl, that moment has been creeping forward on the calendar, slowly, year by year. Trees are waking sooner than they once did, responding to warmer temperatures that come earlier in the year. It is a subtle change. A few days here, a week there, but across entire forests, across continents, the pattern is clear. Spring leaf out is not what it was a century ago. The rhythm is shifting. And the trees respond, because that is what they have always done. They listen to the light. They feel the warmth in the soil. They read the length of the night, and they adjust. But the world is changing faster now than it has in a very long time. And whether the trees can adjust quickly enough, whether their memories and their chemistry and their ancient sensitivity to light will be enough, that is a question the forest ring by ring, season by season. And when the rhythm shifts, even slightly, the consequences ripple outward, far beyond the tree itself. You see, a forest is not a collection of separate lives. It is a web of timing, a delicate choreography where one event depends on another, and another depends on the one before it. When spring arrives earlier than it should, the trees may open their flowers before the insects that pollinate them have emerged. A bee that has timed its awakening to the warmth of late April may find that the blossoms it depends on have already come and gone by the time it stirs from its winter rest. The tree bloomed. The bee was not there, and so the flower closes unpollinated. The fruit never forms. The seed is never made. It is a mismatch, a quiet one. No sound marks it. No visible disaster. Just an absence. A meeting that did not happen. A partnership that has worked for thousands of years, now falling out of step. And it is not only the insects. Some migratory birds travel enormous distances each spring, crossing continents to return to the forest where they breed. Many of them time their arrival to coincide with a very specific moment, the peak of caterpillar activity on newly leafing trees. The fresh young leaves attract caterpillars. and the caterpillars feed the birds, and the birds feed their young. It is a chain built on timing. Each link depends on the one before it. But if the trees leaf out too early, the caterpillars come and go before the birds arrive. The birds reach the forest to find the feast already over. Their chicks hatch into a world with less food, and the forest feels that absence too, in ways that take years to fully understand. All because spring came a few days sooner than it used to. And there is another danger in an early spring, one that the trees themselves must bear. If warm weather arrives too soon, the buds may open. The new leaves may unfurl, tender and green and full of water, and then the cold returns. A late frost, settling over the forest in the dark hours before dawn, can destroy an entire new canopy in a single night. Every fresh leaf, every opening flower, frozen and blackened. The tree survives, but it has spent its stored energy on growth that is now gone. It must begin again, drawing on reserves that were meant to last the whole season. This is the risk of waking too early. And it is a risk that is growing because false springs are becoming more common. Unusual warm spells that arrive in late winter, coaxing the trees out of dormancy, only to be followed by a hard freeze. The warmth whispers that it is time, and the tree listens. Because listening to warmth is what it has always done. But the warmth was a false signal, and the cold that follows is unforgiving. The trees have no way to undo what they have begun. Once a bud opens, it cannot close again. Once the tender cells of a new leaf are exposed to the air, they are vulnerable. And yet, for most of their lives, the frost hardiness of a tree is not a fixed thing. It changes throughout the year, rising and falling like a slow tide. In midsummer, a tree is at its most vulnerable to freezing. Its cells are full of water. Its tissues are soft with growth. But as autumn deepens and winter approaches, the tree gradually hardens itself, building its defenses layer by layer, until by midwinter, it reaches its peak of cold tolerance. Some boreal trees, the spruces and birches and pines of the far north, can survive temperatures below -40 degrees during full dormancy, 40 below, where Celsius and Fahrenheit converge at the same bitter number, and the tree endures it, standing still in the frozen dark, alive. How is this possible? The answer lies in what happens inside the cells. As winter approaches, the tree slowly moves water out of its living cells, drawing it into the tiny spaces between them. If ice forms, and it does, it forms only in those spaces outside the cells, not within them. The crystals grow in the gaps, pressing gently against the cell walls, but never piercing them. This process is called extracellular freezing, and it is what prevents fatal ice damage inside the living tissue. The cell itself remains unfrozen, slightly compressed, waiting, its vital structures intact, its membranes whole. It is a kind of controlled surrender. The tree allows ice into its body, but keeps it out of the places where ice would be deadly. Some trees use another strategy as well, one even more remarkable. Their cells simply refuse to freeze. Even when the temperature drops well below the freezing point, the water inside remains liquid, suspended in a state called supercooling, hovering below zero without forming a single crystal. This is possible because of what the cell contains: sugars, proteins, dissolved compounds that act as a natural antifreeze, lowering the freezing point of the water inside. The more concentrated the solution, the colder it must get before ice can form. And so the tree fills its cells with these protective molecules, quietly, gradually, as the days shorten and the air grows sharp. It is chemistry in service of survival, ancient chemistry, refined over millions of winters. And the tree has one more layer of protection, one you can see with your own eyes and even touch: bark. The bark of a tree thickens with age, adding layer upon layer over the decades. And as it thickens, it becomes a better insulator, shielding the living tissue beneath from the worst of the cold, and the heat, and the fire, and the wind. A young sapling with thin bark is far more vulnerable to a sudden freeze than an old tree with deep furrowed armor. The elder has had time to build its defenses, ring by ring, year by year. Some trees take this to an extraordinary degree. The cork oak of the Mediterranean grows bark that can be several centimeters thick, so thick that it can be carefully stripped away and harvested without killing the tree. The bark grows back, slowly, and the tree continues on. It has been giving up its outer layer to human hands for all of this. The chemistry of frost hardiness, the slow thickening of bark, the timing of bud break and leaf fall. All of it is part of a single annual cycle, a rhythm that the tree follows year after year. But the tree does not follow this rhythm alone. Its annual cycle of growth is synchronized with thousands of other organisms in the ecosystem around it. The insects that emerge when the leaves unfurl, the fungi that fruit when the leaves fall, the birds that arrive when the caterpillars peak, the squirrels that cache their food when the acorns drop. Every one of them is listening to the same seasonal signals, light and temperature and moisture, and every one of them is dancing to the same slow music. The tree is not a solitary performer. It is part of an ensemble, vast and interconnected, where the timing of one shapes the fate of many. And this ensemble has been rehearsing together for a very long time. Consider the squirrel in October. It moves through the canopy with a kind of focused urgency, gathering acorns from the oaks, small triangular nuts from the beeches. It buries them one by one in the soil below, dozens each day, hundreds over the course of a few weeks. The squirrel does not know that winter is coming in the way that you or I might know it, but its body knows. Its instincts are tuned to the rhythm of the seed drop, and the seed drop is tuned to the shortening days. The tree releases its seeds, and the squirrel responds. Two lives, shaped by the same fading light. Down on the forest floor, something else is stirring. The fallen leaves have barely settled before the fungi begin to appear, pale caps pushing through the litter, thin stems rising from the damp earth. Many fungi fruit in autumn precisely because of this sudden abundance. The flush of fallen leaves is a feast for them, a layer of organic matter rich with carbon and nutrients, laid down all at once like a table being set. The fungi break it down slowly, quietly, returning what the tree borrowed from the soil back to the soil again. It is not dramatic work, but it is essential. Without the fungi, the forest floor would simply pile higher and higher, year after year, with nowhere for the nutrients to go. And then the wheel turns, winter passes, the cold slowly loosens its grip, and sap begins to move again through the wood. In late winter and early spring, when the days warm but the nights still freeze, pressure builds inside certain trees, pushing sugars dissolved in water upward through the trunk. This is the same flow that gives us maple syrup, but it also feeds other creatures. Woodpeckers and sapsuckers drill rows of small, neat holes into the bark, tapping into that rising sweetness. The holes are precise, evenly spaced, almost decorative. You can sometimes find them on birches and maples, little grids of shallow wells that fill with sap. The birds return again and again to drink, and insects come too, drawn to the sugary liquid, which in turn draws more birds. A small economy. Not everything in the forest moves at this pace. Some things move so slowly they seem not to move at all. Lichens, those pale green or gray patches on the surface of bark and stone, grow at an almost imperceptible rate, a few millimeters a year in many cases, sometimes less. They are not a single organism but a partnership, a fungus and an alga living together, and they are remarkably patient. Because they grow so slowly, their size can tell us something about time. A large lichen on a rock or a tree trunk suggests that the surface beneath it has been stable and undisturbed for a long while. Scientists have used lichen growth to estimate how long ago a glacier retreated or how long a gravestone has been standing. They are quiet clocks, marking the years in fractions of a centimeter. This impulse to read the timing of living things, to notice when the leaves unfurl, when the flowers open, when the fruit falls, is one of the oldest scientific traditions we have. It is called phenology, the study of seasonal events in the natural world. and people have been practicing it in one form or another for as long as there have been people who depend on the land. In Japan, the blooming of the cherry trees has been recorded for over 1,000 years. Poets and court officials noted the dates each spring, sometimes in diaries, sometimes in official records. These observations were not made for science. They were made out of love and ritual and attention. But when modern researchers gathered those records together, they found something remarkable. The cherry blossoms have been arriving earlier, gradually, over the centuries, and the shift has accelerated in recent decades. 1,000 years of handwritten dates, telling a story about a warming world, long before anyone had a thermometer precise enough to confirm it. On the other side of the world, in a small cabin near a pond in Massachusetts, a man named Henry David Thoreau was doing something similar. In the 1850s, he walked the woods around Walden Pond and wrote down what he saw: the date the first hepatica bloomed, the day the red maples began to leaf out, the moment the huckleberries ripened. He recorded these things with care, not as a scientist exactly, but as someone who believed that paying attention to the world was a form of respect. More than 150 years later, modern scientists found his notes, and they compared his dates to what they observed in the same woods, in the same seasons. The results were striking. Many of the plants Thoreau watched now bloom days or even weeks earlier than they did in his time. His quiet observations, made with nothing more than a pencil and a notebook, became one of the clearest records of climate change in New England. A gift. Today, we watch the seasons change from much farther away. Satellites orbiting the Earth track the greening and browning of forests across entire continents in real time. They measure something called the Normalized Difference Vegetation Index, which is essentially a way of asking, how green does the land look from space? When spring arrives in the northern hemisphere, the index rises as millions of trees push out new leaves, and when autumn comes, it falls again as the green fades to gold and brown. From orbit, you can watch the seasons roll across the planet like a slow green wave, moving northward in spring, retreating southward in autumn. It is a view that no single person on the ground could ever have, and yet it confirms what the cherry blossom records and Thoreau's notebooks already told us. The timing is shifting. Spring comes a little sooner, autumn lingers a little longer. The rhythm is changing. But not all trees follow the same rhythm. In the tropics, where temperatures stay warm year-round, the seasons are not defined by cold and heat. They are defined by water. Tropical trees that experience a distinct dry season may drop their leaves, not because of frost, but to conserve moisture. The trigger is different, but the response is strangely familiar. A tree shedding its canopy, waiting, and then growing it back when the rains return. The baobab trees of Africa have taken this strategy to an extraordinary place. Their massive trunks, sometimes wider than a small house, are not filled with dense wood. They are filled with water, stored during the wet season and drawn upon slowly during the long dry months. A baobab can hold thousands of liters inside its swollen trunk, enough to survive in landscapes where rain may not fall for half the year. They stand on the dry savanna like ancient water towers, patient and immense, waiting for the clouds to return. And then there is the ginkgo, a tree that has remained nearly unchanged for over 200 million years. It was already old when the dinosaurs were young. Its fan-shaped leaves have been found pressed into stone from the Jurassic, looking almost identical to the ones that fall in city parks today. The ginkgo has watched ice ages come and go, has survived mass extinctions, has outlasted entire lineages of animals that once sheltered beneath it. And still, every autumn, its leaves turn a clear, bright yellow and fall. It does not hurry. It does not worry. It simply remembers what to do, the way it has always remembered, season after season, for longer than we can comfortably hold in our minds. There is something almost startling about the way a ginkgo lets go. Most trees release their leaves gradually, a few each day, scattered by wind and rain over the course of weeks. But the ginkgo does something different. It holds on and holds on. And then, often within just a few days, it drops nearly everything at once. The ground beneath a ginkgo in late autumn is a perfect circle of gold, as if the tree laid down a quiet offering over. Most conifers never do this at all. They keep their needles through every season, dark green against the snow, steady and unchanging. But there is one that breaks the rule. The larch is a conifer that behaves like a deciduous tree. Every autumn, its soft needles turn a deep, warm gold, and then they fall, all of them, leaving the branches bare and pale against the winter sky. If you did not know better, you might think something was wrong. A conifer without its needles looks unfinished somehow, exposed. But the larch is not struggling. It is simply doing what it has always done, choosing to let go, where others hold on. It will grow them all back in spring, fresh and bright and impossibly soft for a needle-bearing tree. There is a quiet courage in that, in being the exception, in finding your own way through the cold. And then there are the trees we thought were gone forever. In the early 20th century, scientists knew the dawn redwood only as a fossil. Its delicate feathery leaves were pressed into ancient stone, millions of years old. It was studied the way we study dinosaurs, with respect and a sense of finality. It belonged to the past, or so everyone believed. Then, in 1944, in a remote valley in central China, a living dawn redwood was found, standing quietly among the hills, as if it had been waiting to be noticed. It had not gone extinct after all. It had simply been growing, somewhere out of sight, in a valley that the wider world had overlooked. The discovery was met with a kind of stunned reverence. Here was a tree that the fossil record had declared finished, and yet it was still putting out leaves each spring, still dropping them each autumn, still breathing, still remembering the seasons, as it had for millions of years before anyone was counting. Not all trees mark the seasons so visibly. Along tropical coasts, where the air is warm and wet throughout the year, mangrove trees grow in the space between land and sea. Their tangled roots reach down into salt water and mud, and they do not pause for winter, because winter never truly comes. They grow year-round, slowly, steadily, without the dramatic rhythms of temperate forests. But even mangroves carry subtle signatures of the seasons within their wood, slight variations in growth rate, faint density changes tied to monsoon cycles, or shifts in salinity. The seasons whisper to them differently, not with frost and falling leaves, but with tides and rain and the slow pull of the moon on the water around their roots. They listen in their own way, and they remember in their own way, quietly. At the other end of the earth, near the Arctic tree line, trees live at the very edge of what is possible. The growing season may last only a few weeks. The soil thaws just enough for roots to drink before freezing again, and in that brief window of warmth and light, a tree may add only a fraction of a millimeter of new wood, a ring so thin you would need a microscope to see it clearly. These are not grand trees. They're often small and twisted, shaped by wind and cold into forms that look more like sculpture than forest. But they are alive, and they are growing. Even if the pace is almost too slow to measure, each ring is a whisper of a summer that came and went, a record written in a language of patience we can barely comprehend. And perhaps the most patient of all is a forest that is not really a forest, at least not in the way we usually think of one. In the mountains of Utah, there is a grove of quaking aspens known as pando. From above, it looks like thousands of individual trees, their white bark catching the light, their small round leaves trembling in the slightest breeze. But beneath the surface, they are all connected. Every trunk in the grove rises from a single vast root system. They are not separate trees. They are one organism, one living body, spread across more than 100 acres. Pando has been growing and regenerating for an estimated tens of thousands of years. Some researchers believe it may be far older than that. It was ancient before the pyramids were built, before the first cities rose along the rivers of Mesopotamia, before humans learned to write down the things they wanted to remember. And every spring, its roots send up new shoots. Young trunks rise from the old network below, reaching for the light, continuing a cycle that is older than most civilizations. When one trunk dies, another takes its place. The root system endures, patient and vast beneath the soil. It does not need any single trunk to survive. It only needs the ground to thaw and the light to return, and it begins again. A forest in autumn is not dying. It is preparing, sealing its leaves, storing its sugars, pulling its water deep, settling into a stillness that only looks like emptiness. Beneath the bark, the buds are already formed, tiny leaves folded tight, waiting. Beneath the soil, the roots are still connected, still sharing, still holding on to each other in the dark. The cold will come, the snow will fall, and the trees will stand quietly through all of it, the way they always have. Not because they do not feel the season changing, but because they remember what comes after. The light will return. It always does. And the forest will begin again. Slowly, softly, the way it always has.